Okay, let's do one more example of our hypothesis testing procedure, just because this is the foundation, really, of using the tools that we have in our statistical toolbox for answering research questions. That is, we're making inferences based on what we find in our statistical analyses of research data. Okay? So let's do something, and I want to use this example because maybe it's a little bit more higher tech, or somebody might be a little bit intimidated by the some neuroscience information. But we're going to use the same exact procedure to make our decisions about some research manipulation. So let's do this. Let's suppose that we know, and we will get away from the givens because oftentimes with research we don't start with these with being provided with this information. But for now, we're going to do this, and then we'll make another step, and then we'll make another step as we've done in the past. So let's assume that normally, under normal circumstances, we know that neurons in a particular part of the brain, let's say the hippocampus, because you can actually extract some cells from the hippocampus intact, and you can measure the cell firing. Okay, so we're going to put an electrode in these neurons and measure how fast the neurons fire signals. Okay, so let's assume that normally we see, let's say, 50 impulses per second. Okay, or let's make that per minute. Okay, let's make that per minute. 50 impulses per minute. When we look at these neurons, we of course know that not all neurons are average, just like not all people are average, and not all dogs are average, and not all leaves on a tree are average. That is, that there's going to be some variability. And so let's say on average about 50 impulses per minute, and we'll say that the standard deviation is 9. Okay? And perhaps a neuroscientist wants to, with this hippocampal cell preparation, they want to know if calcium affects the neural impulses, the rate at which these neurons fire. Because we know that calcium is a positively charged ion that's involved with lots of cellular processes and probably would affect neuronal functioning. And so we're going to add some calcium to the bath, the petri dish where we have our cell preparation. Okay? And so from that information, we can create our research hypotheses, and we can say, we'll set up the experimental hypothesis, also called the alternative hypothesis, because it's an alternative to the null. Okay, we say that when we give the cells calcium, what we're going to do is we're going to create a population, this is hypothetical, that will be different than what we see under normal circumstances. Okay? Another way that we can write this is we can say the population that gets calcium is going to be, the cells are going to fire at a rate that is different than 50 impulses per second or per minute. Okay? So two different ways that we can write this. The null hypothesis then would say that calcium does not have an effect. That is, that we're going to see the same kind of firing that we do when cells are just in a normal situation. Another way to write that would be that they're going to have an average of about 50 impulses per minute. Okay, so that's a step one for our hypothesis testing procedure. Step two would be, of course, setting your alpha level. And again, this is the extreme where we're going to make a decision about whether to reject the null or not. That is, we're going to wait if the cells, if after we put the calcium in, they're out in the extremes of what would be considered normal firing rate. If they're in the extremes, then we're going to make an inference that the calcium had some kind of an effect. Okay? And this alpha level is associated with a z-score of plus or minus 1.96. So this should be all review. Okay, this is all stuff that we've talked about before. That's why I'm not spending too much time on either of these steps or any of these steps. Step three would then be to collect the data, and let's say that we're going to use, let's say we have 12 neurons that we're looking at. We're going to check their firing rate. And the average for this group of 12 with the calcium, okay, the average for this group of 12, and I'm going to need to back calculate a little bit here in my head. So let's say that, well, we'll do this. Let's say that the firing rate for these cells is 61.33 impulses per minute. All right. Now, just a reminder, I want to know if this is different from this, okay? But we're not just doing arithmetic. We're doing our decisions based on probabilities, because even when the mean for these cells is 50, is it possible to get something like this as a mean? Well, I would say everything's possible. We want to talk about probabilities, okay? And I also am going to point out here that over here we're talking about populations, right? And here we have a sample. Here's another level of the inference that we're doing. We're assuming that when we put our proverbial hand into the canvas bag and we pull out of 12 neurons and we look at the average for those 12 neurons, we're going to assume that they somehow represent the population. Okay? So we're going to use the mean for a sample of 12 to make some kind of guess about the mu, the population of cells that would be bathed in calcium. Okay? That's our inference. The population of cells bathed in calcium is a hypothetical population. It doesn't really exist. And we're going to say hypothetically that it involves an infinite number of cells that would be or could be bathed in calcium and so on and so forth. Okay, this is all abstract kind of stuff here. Now, I'm not going to draw the curve again. If you need to see that, you can review the previous video. But we know our test statistic here is going to be a z-score. And let's remember the structure, the conceptual structure of the z-score. The conceptual structure of the z-score. We're going to take our mean for the calcium. We're going to compare it to the mean of the samples of normal neurons, okay? Even though this is subscripted with calcium, we're trying to make a decision. Do they look like they're normal, right? Do they look like they're normal? So I'm going to compare this to what I would see normally for samples of 12, taken from here, and then divided by the standard deviation of that same sampling distribution. So we're talking about the sampling distribution of this population with sample size 12. because that's what I have for my calcium. So I want to compare a sample of 12 to all the samples of 12 divided by the standard deviation of all the samples of 12 of these neurons. Okay, everybody with me? The question is, does this look like it comes from here? So we're going to use those parameters. So the z-score here is going to be 61.33 minus 50, because that's the mean of our sampling distribution of means will always equal the mean of the distribution of individual scores from which the samples were taken. You see how that concept, we need to maintain that concept in our memories, and that's why I'm reminding you. So this is what the mean of the sampling distribution of sample means of 12 would look like from this population. Wow. Take your time. Think about it in a stepwise fashion. We need to compare that to the standard deviation of the sampling distribution of means from here, which is 9 divided by the square root of 12. Okay, so let me get my handy dandy here. 12, we're going to take the square root, 3.46, okay? So 9 divided by 3.46, 2.60, okay? So this ends up being 2.60. Let's calculate our z-score then. 61.33 minus 50 equals, divided by 2.60 equals, wow, a z-score of 4.36. 4.36, okay? So the question here, and I'm going to let you think about it for a minute, right? Do we reject the null or do we fail to reject the null? Well, the null says that the population of cells bathed in calcium is going to be the same as normal. But what we're seeing here is, if this was the case, we would expect the calcium average to be about 50. Now we know there's going to be variability. That's just too far out. 4.36 standard deviations away from 50. And so in this case, I'm going to reject the null. And let's do this as step 4, right? Reject the null. I don't think that this is the case. Okay? And now, step 5, it appears that adding calcium to the, what do we want to call it? Adding calcium to the bathing solution, because these cells are going to be in a solution, okay? Significantly increases the firing rate. And again, I'm going to erase this for now. Again, I want to tell the reader, tell myself, write in the journal report, whatever it is, your audience. So a Z of 4.36, is that what we said? Which is, make sure the period goes after the parentheses, okay? So I'm saying that the probability of the null hypothesis being true is less than 5%. And with such a large z-score, again, if I had done this research and was publishing this, I would put p less than 0.01 here, because this certainly surpasses that level of significance as well. Again, for our class, this is fine with me, okay? And those are the 5 steps. Okay, so this should be review, I hope. But now I want to go further. Okay? And please email me if you have questions about this. Or you can, like watch the video again, write down your questions, let me know if you have them. So what we're saying is we're going to reject the null. I don't think that the population of these neurons bathed in calcium, I don't think it's equal to 50. In fact, if we look at our alternative hypothesis, it said that the calcium is not equal, the firing rate of calcium is not equal to 50 impulses per minute. So it's telling me what it's not, but of course, what I want to know is what it is, okay? I mean, if it's not 50, what is it? You see, this is the next step, right? I mean, if you used a dictionary to look up a word and you said, well, I want to know the definition of giraffe, and you looked up in a dictionary, it said a giraffe is not a cow. I'm like, okay, but what is it, right? A giraffe is not a dog. Okay, but what is it? A giraffe is not a car. All right, but what is it? You see what I mean here? We're saying we don't think that the calcium, the mean for the population now, we don't think it's 50. And so the next question would be, well, what is the mean then? Any guesses? Well, my guess would be that the mean for the population is 61.33. Now, let me clarify here. This is the mean for the population of cells that would be bathed in calcium. Okay? What I'm saying is my guess for this is the same value as here. Now we need to think back 2 or 3 videos ago. Remember when we put our hand in the bag and we picked out that single block? Our guess for the population that's in that bag, our guess was the value of that single block. But the rationale was not just because it was the only thing that we had. The rationale, it's a very strong rationale here, is when I put my hand in the bag, the most probable pick that I have will be at the mean, because the mean is also the mode. So it's the most frequent, it's the most probable. So again, this is an abstract concept, right? I sort of put my hand in the bag and took out 12 neurons, and I got this for the mean. So this will end up becoming my guess for the population. Now, could I be wrong? The answer is sure, I could be wrong. But based on what we know about probabilities and the quincunx and all of the stuff we've been talking about, this would be a pretty good guess, even though we're going to admit that we're wrong, okay? And by the way, this is a little admission that we could be wrong right here. We're saying the probability that this is the case, the null hypothesis, is less than 5%. We're not saying that it's 0. We're not saying that it's 0, okay? So this is my guess, my inference. That's why it's called inferential statistics. But of course, to describe a population, I want to know the mean and I want to know the standard deviation, right? Our gold standards. So the guess for my mean for the population is 61.33 based on the sample. What about my guess for the calcium standard deviation? Well, this is a tough one. But if we go back to chapter 4 in the textbook, there's a little thing in there that was kind of interesting, and we talked about this when we talked about sum of squares. The size of the mean is not what we're talking about when we talk about variability. We're talking about spread outness, right? And here's an interesting thing. If I take a group of numbers, let me do this just as a little sidebar here. If I take a group of numbers, let's say 5, 6, 8, 10, 15. I mean, we could calculate the sum of squares for this. We could calculate the standard deviation, right? I mean, you guys can do that now. And it's a good thing. You're really learning a lot. If I add 5 points to each of these, 5 points, so we have 10, 11, 13, 15, and 20, and you can try this if you want. The standard deviation for this group and the standard deviation for this group will be exactly the same. If I add a constant or subtract a constant from a group of scores, the mean will change. The mean for this is certainly different than the mean for this, right? And you guys, I would encourage you to do that. Get the mean here, get the mean here. It's going to be different. Get the standard deviation here, standard deviation here. It will be exactly the same. When we add a constant, whether it's positive or negative, the standard deviation for a group of numbers stays the same. Okay? Fact. Based on this knowledge, what we're going to say is we're going to assume that a treatment effect, that is, if we add calcium, we're going to go from an average of 50 impulses per minute to an average of 61.33 impulses per minute. That's what we would call the treatment effect. On average, it's increasing impulses by 11.33 impulses per second. Okay? So the treatment shifted the curve, but what we're going to assume is it's effectively adding a constant. So there's going to be slow neurons here, under 50, but we're expecting they're going to go up by about 11.33. There's going to be fast neurons here, maybe 70 impulses per minute, and they're going to go up by 11.33. In other words, the treatment will add or subtract a constant to every score, and if we do that, the standard deviation will remain the same. So this is my guess for the population parameters for neurons that are bathed in calcium. This would be my guess. Based on my z-score, that was also based on the central limit theorem. That's how we got this. We thought the probability is the highest that we're grabbing the mean from this unknown population. You see, this is what makes the course, for me, exciting, but difficult sometimes because you have to bring all of this information with you, put it together, and I hope that how I'm presenting this helps. Putting it together, now using it as a very powerful tool. Okay? This is our guess. I could be wrong. Okay? In fact, that p less than 0.05 means that maybe the null hypothesis is actually true. The probability of that happening is less than 5%. So I'm going to reject it. But I'm going to acknowledge that this is not proving anything. It's just a high probability that I'm correct. Okay? So that's what I want to talk about next. And we're going to get rid of these specific examples. But we'll need to think about these examples when we think about inferential statistics and, in fact, making guesses when you don't know all of the information. Okay? And so we're going to try to make the best guess that we can, but we're always going to acknowledge that we could be wrong. And let me give you an example of that's sort of not statistics related first, and then we'll talk about statistics more specifically in some of the abstract sort of jargon with the null hypothesis and so on and so forth. Listen, meteorologists do inferences all the time. It's called weather prediction, right? And so what they do is they try to predict whether or not, we're going to have a storm, or whether it's going to rain, or whether it's going to be, whatever the prediction is. And so what they're trying to do is, tomorrow we will have some reality, right? Tomorrow there will be some reality. I mean, it's called the truth, I mean, tomorrow it's either going to rain or it's not going to rain, okay? And those are the two possibilities, right? It's either going to rain or we're going to have no rain. So that's the reality. What the meteorologist is trying to do, so over here is the meteorologist. Can you see that? Meteorologist. Wow. Okay. Here's the prediction that it's either going to rain or we'll have no rain. Okay? Now, the meteorologist is not going to roll dice and make that decision. The meteorologist is not going to look into a crystal ball. What is the meteorologist going to do? Collect data. What's the temperature today? What's the wind speed? What is the air pressure? What are the circulating patterns of the jet stream, and so on and so on and so on. Okay, I mean, they use lots of real high-tech data to make this prediction about what will happen tomorrow. And what you find in this case and pretty much with all inferences is that you have this 2x2 matrix. By the way, little secret here for college courses. If a professor sets up a 2x2 matrix, that's very important, okay? You should pay attention. These 2x2 matrices usually represent sort of a cross about what is going to be reality versus what a prediction is, okay? Or if you've done Punnett squares in biology, you're going to be set up with this matrix for whether or not we're going to see the disease in an offspring or something like that, or blue eyes or brown eyes or wrinkled peas or smooth peas. This is all genetics stuff. Same kind of a thing. But here is the matrix. Okay, and what we're going to do for each of these matrices is figure out how the prediction ends up matching reality. Okay, so if the meteorologist predicted rain and it ends up raining, well, then the meteorologist was correct, right? And we're going to call this a hit. I'm assuming that some of you have played Battleship before. Have you ever played Battleship? Right, you put your ships and then the person guesses, I'm going to guess B2 or, D3 or E12. And then you tell the person whether their guess matches reality. And that means if that guess matches reality, then you have a hit. They're correct. And if the person's guess doesn't match reality, well, then it's a miss, okay? It's the same thing here, except meteorologists are certainly making predictions based on data. When you play Battleship, it's usually just sort of random guessing, okay? It's just kind of weird. So the meteorologists, they predict rain and it rains, they are correct. If they predicted rain and there's no rain, well, then this is called an error or a miss, okay? If the meteorologist predicts no rain, but it rains, Well, this is also an error, a miss, okay? If the meteorologist predicts no rain and it doesn't rain, of course, then we have a correct decision or a hit, okay? And in fact, whenever a prediction is made, there are these four possibilities, two that are correct, two that represent an error, okay? And by the way, let's turn this from rain to snow, okay? Because this is one of my pet peeves that I'll talk about. So let's do this. Snowstorm, right? No snowstorm. This is a snowstorm. No snowstorm. And of course, we can still talk about meteorologists predicted a storm. Storm came. Meteorologist was correct. Meteorologist says snowstorm. No snowstorm came. That's an error. Just like no snowstorm, but a snowstorm really came. That's an error. They predict no snowstorm, and no snowstorm came. That's correct. Now, of course, we want to be either here or here, right? We want to be correct. But when we do inferential work, when we make a prediction, when we're guessing, we don't know if we're correct or not. Otherwise, why would you be guessing, right? So we never know if the meteorologist doesn't know if they're going to be correct when they make a prediction about the next day's weather, okay? Of course we want to be correct, but very important here. This is one of my pet peeves, so pay attention. Sometimes people will say, oh, they predicted a snowstorm and it never came. Oh my God, they predicted a snowstorm and it never came. All right, well, that's an error. I'm always amazed at how accurate weather predictions are for the most part. I'm a golfer, and sometimes I look on the intrawebs and it says, the rain should be arriving at around 3 o'clock. And I'm like, oh my God, I want to get out and golf before then, but I can't get out till 2. Well, maybe it'll come, maybe. I swear to God, half the time I'm out at a golf course, and it's like they predicted rain at 3. It's like 3:15, here comes the rain. I mean, I'm just amazed, but a lot of people, I don't know. Again, this is one of my pet peeves. People complain about weather people all the time, and I'm like, well, then you should try it, because I'm always impressed. Anyway, I digress a little bit. Weather prediction is the storm never came, and that's an error. Well, there's another error. Meteorologist predicts no snowstorm, but then a big storm comes. That's an error. Here's my question to you. Of course we want to be here or here. I want the weather person to be correct. But if they're going to make a mistake, which is there one of these errors that's better than the other? Take a minute to think about this. Are both of these created equal? That is one of these worse than the other? The answer is, of course, one is worse than the other. I would rather have a meteorologist predict a snowstorm and then not have it come than to not predict a snowstorm and we get nailed. Okay? Why is this a better error? Well, if the meteorologist predicts a snowstorm and none comes, well, there's no damage. And any preparation that you might have done is, that's okay, right? You might have gotten up a half hour early to shovel your driveway or something like that, but there was no storm. All right, well, you get an extra half hour. Or they predicted a snowstorm and it never materialized, well, there's not going to be any, damage. But listen, if they predict no snowstorm, you might have decided you're going to travel to somewhere, drive for 3 hours, but then all of a sudden a snowstorm came. It's like, oh my God. Or they predict no snowstorm, and so you just got up at your regular time. Now you got to shovel the driveway just to get out, and so you're going to be late, so on and so forth. So I would say that this error, of the two errors, this one is worse, okay? Because you're not prepared. Yes, this is an error as well, but it doesn't have as many consequences, okay? So, and by the way, I absolutely can tell you that meteorologists learn the difference between this error and this error. If they're going to make an error, you better be safe than sorry, okay? You're better to be safe than sorry. And so there is a bias, that is, if the meteorologist thinks there might be a snowstorm, you're better off predicting a snowstorm than saying no snowstorm. Okay? We want to be here, of course. We want to be here or here. We want to be correct. But if we make a mistake, there's usually an error that has more serious consequences, okay? I mean, when a doctor makes a medical diagnosis, they are making an inference, okay? Because in reality, let's do this. I mean, in reality, you either have the disease, right? Or you don't have the disease, or sickness, or whatever it is. The physician is going to say, well, either you have the disease or you don't, right? I mean, medical science has gotten so good because it's based on our knowledge of physiology, it's based on data. The medical science has gotten pretty good, so we think that it's not an inference when a doctor makes a diagnosis, even though it is. And how does the doctor make the diagnosis? Based on data. What's your body temperature? What's your blood count? What is your blood pressure? What are your symptoms? So on and so forth. And so then they'll make this decision. Well, yeah, believe it or not, here we go, okay? Doctor thinks that you have the disease. You really do. So this is correct, right? This is a hit. But it's not a good hit. I mean, nobody wants a disease, but in terms of matching the diagnosis with reality, the doctor says you don't have the disease, but you really do. That certainly is a miss. The doctor says you have the disease, but you really don't. Doctor says you don't have the disease, and you don't. So this is correct here too. Okay? Want to be here? Want to be here. I mean, I really don't want to be here personally. In terms of our decision making, here's where our decision matches reality. Here's where our decision matches reality, right? But there are two errors in this case. Can you identify which error would be the worst error of the two? Well, I would rather have the doctor tell me I have the disease and later find out I don't. I would rather have the doctor say, I think you have this disease, we'll start the medication, but you really don't. Okay, cool. Now, it gets a little bit more difficult to identify the better error because when you have cancer, for example, because the treatment for cancer is pretty serious stuff and it can cause its own complications. But for mild disease, I'd rather be told that I have it and then find out that I don't than the doctor saying you don't have this disease and finding out that I really do, because then I've missed out on the potential treatment, right? And so this is the better error in the case of the doctor's diagnosis, okay? Now, some people are going to say, well, why did they say you have the disease when you don't? Because the doctor has incomplete information. It really is an inference, okay? Why would the doctor say you don't have disease when you do? Well, because the symptoms aren't showing yet, or the symptoms were different than what the doctor thought, or maybe you didn't report it accurately, or whatever. There's reasons to make a faulty diagnosis because the doctor can't see reality. The doctor can only make guesses. It's an inference. With the meteorologist, of course, we don't know what's going to happen tomorrow. It's impossible in that case. But hopefully the doctor, your meteorologist, know what data to look at, what data to collect to make a good decision. Okay? So this happens all the time. It happens in a court of law as well. Let's do this. The person either committed the crime or did not commit the crime. I mean, that's the reality, right? So we have somebody in a jury situation. They've been accused of the crime, but of course, we don't really know the reality, right? You can watch any television show, your favorite crime or your crime novel or a television show. They're trying to figure out reality. Did the person commit the crime or did they not commit the crime? And of course, then what we have to do is we have a jury, and the jury makes a decision based on data. It's called evidence, right? That's information. Data is information. It's evidence in a court of law, right? And so the jury will say the person committed the crime. That is, they'll say they're guilty, or they'll say they did not commit the crime. They'll say not guilty. You ever wonder why they don't say innocent? They never say innocent. They either say guilty or not guilty, right? Because you can't prove a negative. All right. Anyway, this sets up, once again, a nice matrix. Okay. The jury says, we think the person committed the crime based on the evidence. And the person committed the crime. Okay, this is correct. By the way, I can move these descriptors around and make the correct and the error in different quadrants. It's not always that this one's correct. Please don't memorize some position. It's whether the decision matches reality, right? So correct here. Jury says the person committed the crime, but they did not commit the crime. Uh-oh, this is called an error, right? Now again, please, please, please use your good brain, okay? Because sometimes people say, well, why would they say the person committed the crime when they really didn't? Well, listen, folks, it happens. It happens, okay? You were at Nice and Easy last night, some convenience store. You were at the convenience store. And the convenience store got robbed and the clerk got murdered. And there's videotape. You were there. And you have blood on your clothes. It's like, yeah, because I was there. There was blood splattered all over the place. You got blood on your clothes. You were there. You went speeding off right afterwards. Well, because you were scared and you didn't want to get hurt yourself, right? And then they look at your cell phone and there's some text that says to the clerk, I'm going to kill you because you're going out with my boyfriend or my girlfriend. And you're like, yeah, I was just saying that. I didn't mean I was going to kill them. Well, it's right there. And so the jury might commit you, say that you committed the crime. You're like, I didn't commit the crime, right? Based on the data that is imperfect, a jury may say that you committed the crime, when you really didn't. That was an error, okay? That happens. This is why I'm opposed to the death penalty. It's not a political stance. For me, it's statistical. Because I know that this kind of error can happen. And if you kill the person, you can't undo that, okay? There was a person in my hometown that spent about 20 years in jail for murder. And then he was exonerated based on DNA evidence so many years later. And they figured that he did not commit the crime. But if they had given him the death penalty, he wouldn't be around. Okay. Anyway, for me, it's a statistical issue, not political. If the jury says you did not commit the crime, but you really did commit the crime, and again, why would the jury say this? Well, there's not enough data. There's not enough evidence to say they committed the crime. But that can happen when the person actually committed the crime. So this is an error. If the person did not commit the crime and the jury says, we don't think the person committed a crime, here's the correct. Same thing. Now, ideally, we would like to be here or here. That is, all I want to see and all we want to see in the justice system is for the jury to match reality. Okay? Did not commit crime, did not. Committed crime, committed crime. That's where we want to be. There's two errors. Which one do you think is worse? Now, take your time. This is a tough one. And unfortunately, not enough students learn about the criminal justice system, the basics, in high school, unfortunately. So which one is the worst error of the two? Okay? The juror says, do not commit the crime, and the person really did commit the crime, that's a mistake, or say committed the crime when they really did not. Well, this is the worst error, folks. Now, oftentimes people say, but I don't want a guilty person to go free. I don't want a guilty person to go free. Neither do I. Everybody with me? Because I get nervous about having this on video. I don't want a guilty person going free either. That's what this is. And I would rather be here than here. Everybody with me? I'd rather be here or here. If I'm going to make one of these errors, what do I want to avoid? I want to avoid putting an innocent person, like you, presumably, I want to avoid putting an innocent person in jail. An innocent person in jail. In this country, that's what the basis of our justice system is. I don't want to let a guilty person free, but I don't want to put innocent people in jail. That's the worst error. And in fact, the judge will tell you in a jury trial, if there's a reasonable doubt, that is, a lot of evidence makes it look like the person committed the crime, but if you have a reasonable doubt, then this is where you want to be. What the judge is doing is they're biasing you to make this decision. Okay? They hope that you're correct, but this is the better error. We don't want to put innocent people in jail. Okay? This is something that people don't learn about regularly, and it scares me because I'm innocent and I don't want to go in jail. Okay? Even if I'm in that position where a lot of circumstantial evidence makes it look like I'm, might be guilty. The judge will tell you, if there's a reasonable doubt, you need to do this. If there's a reasonable doubt, you need to do this, because they want to keep you either correct or in this error. Now, the judge doesn't tell you never say guilty, because we do want to be here or here, and this is the better error. Okay? Excuse me. This is the better error. This is the worst error. Putting an innocent person in jail. We're going to bias toward this. Okay, next video we'll talk about how we create this matrix for our research decision making, because it's going to be a similar 2x2 matrix.